Hello everyone. My name is Alex Krasnok, and the theme of my presentation today is Quantum Nonreciprocity with Nonlinearity and Weyl semimetals. Well, since last fall, I have been an assistant professor at the Florida International University in the heart of Miami, Florida. Here is the web page of my lab for quantum technologies and metamaterials. So, as you can see, we're conducting research in quantum materials, sensors, functional meta devices, and other related areas. I want to announce that I am currently seeking motivated students to join my research group, and if you are interested or aware of anyone who might be interested, please pass along this information. To begin with, let me describe the motivation of our work. So we all know that conventional computers can handle problems within the polynomial class without too much difficulty. However, there is another important class of problems, namely non-polynomial problems, that cannot be solved by conventional computers. Examples of such problems include factorization of large numbers, unstructured data search, first principle calculations of atomic quantum spectra, first principle design of materials and chemical elements, and many other vital problems. Well, most of these non-polynomial problems could be solved by a powerful enough quantum computer. Indeed, for most of these problems, the corresponding quantum algorithms already exist. However, the execution of such algorithms is challenging due to the lack of powerful quantum computers. So today, the way we create quantum computers is mostly based on so-called quantum circuits. Consider, for example, the LC circuit. If we cool it down below the critical temperature, the circuit becomes virtually lossless. However, even at these temperatures below 10 Kelvin, the resonator is still populated with many noisy thermal photons. To get rid of them, we cool it much more in the microwave regime, for example, of a few gigahertz. This happens at temperatures below 100 millikelvins. In this case, the resonator is virtually not excited, and we can control the number of photons in it. So in order to work in the two-level regime and realize a quantum bit or a qubit, we introduce the nonlinear inductance based on Josephson junction. A Josephson junction is a contact of two superconductors with an ultra-thin layer, nanometer thick layer of a dielectric that allows tunneling of supercurrent. This technique is well established now, and basically we know the mechanisms of dissipation and dephasing and can control them up to some extent. Then this element can be coupled to excitation, readout, and controlling elements to realize a quantum circuit. We can also couple two or more such qubits, like this one, to enable quantum entanglement of two qubit operations, basically. However, this approach faces a number of serious challenges. The main one is the lack for reliable qubits with long dephasing lifetimes. This plot, for example, shows the progress in this direction over the last 20 years. We can see the remarkable growth of the qubit lifetime over 6 orders of magnitude. Future development relies on the so-called three-dimensional qubits and quasi-three-dimensional qubit architectures. However, even record values are still too short to run long quantum algorithms. Another challenge is associated with the poor scalability of the microwave hardware. More qubits require more and more connectors and microwave equipment, cables, waveguides, and so it's not well scalable. And in my research lab, we recently launched a research program to address these challenges. Another challenge is the main focus, which is the main focus of my talk today, is the need for efficient magnetless non-reciprocal elements, namely insulators and circulators in the readout part of the quantum computer. We use these elements to prevent room temperature noise from going down to the quantum chip from the microwave measurement equipment over here. So this requires unidirectional signal propagation, usually achieved with magnetic bias. However, magnetic fields are harmful to superconducting elements. They are lossy and these elements bulky, and so they are basically another source of extra noise, right? So there are three main approaches to magnetless non-reciprocity today. The first one is non-reciprocity combined with asymmetry, like shown here. Another one is active devices, for example, unidirectional gain, and of course time modulation. However, one should note that the one based on nonlinearity can work only as a two-port isolator, but not as a circulator. In our recent work, we have considered the approach based on asymmetric nonlinearity in a system of two qubits coupled to a waveguide, like shown here. The nonlinearity is enabled by the saturation of the two-level systems, two-level qubits, and the asymmetry is due to the frequency detuning. The James Cummings Hamiltonian of the system consists of the intrinsic Hamiltonian of the qubits, the Hamiltonian of the waveguide modes, and the coupling Hamiltonian in the system. To analyze the system, we have numerically solved the Lindblad master equation with the realistic decay factors gamma over here, and computed the transmission and reflection coefficients in both propagations, left to right and right to left. The results of the calculation are presented here. The transmission is shown in blue and isolation is shown in red for three different values of frequency detuning. So we observed very strong isolation at the level of 40 dB, along with a high forward transmission of 60%. Our more detailed investigation shows that the non-reciprocal response in the system arises due to the weak interaction of the dark state with the field of the waveguide. This effect is associated with the so-called dark quantum state and also known as the quantum embedded eigenstate. The variation of system parameters allows the opening of this state that manifests itself as the asymmetric Fano resonance. In our work, we have taken another step forward and have investigated the temporal modulation of the level of one of the qubits in the system. Well, remarkably, this non-reciprocity effect was realized recently in a waveguide geometry with two detuned qubits, like shown here on this picture. In the group of our collaborators by Professor Arkady Fedorov, the good isolation and high forward transmission indeed have been observed experimentally, demonstrating the potential of such a system for realistic quantum systems. Another approach to quantum non-reciprocity we have also been very interested in is the one based on so-called new topologically non-trivial materials such as Weyl semimetals. Well, a Weyl semimetal is a material that has a three-dimensional Dirac cone split into two Weyl nodes by lifting either spatial or temporal symmetry. Such Weyl nodes are topologically protected because they can be destroyed only by merging nodes of opposite charge. Remarkably, such materials possess strong intrinsic non-reciprocity effects due to strong spin-orbit coupling, often without the microscale magnetization of the entire material. In our work, we have designed a system consisting of a dielectric resonator, shown in blue, sandwiched between two Weyl semimetal slabs, shown in gray. We assume also that the Weyl semimetal slabs they are asymmetric in plane due to natural anisotropy or artificial corrugation. As a result of the intrinsic magnetization and the resonance of the dielectric, the system demonstrates strong isolation under certain geometric parameters. The electric field in this design is localized in the dielectric, making the design loss effective. Because the most of the electric field is localized in the virtually lossless dielectric in this system. Remarkably, the design provides also strong tunability by relative rotations of the layers due to the in-plane asymmetry of the Weyl semimetal layers. Moreover, due to the intrinsic anisotropy of the Weyl semimetals, we can remove one of the polarizers in this geometry, which makes the design more compact. Finally, removing both polarizers enables a so-called polarized insulator when the device isolates one of two polarizations. Basically, this slide shows the result of the full wave numerical simulation of this scenario. We observed full transmission of the polarized polarized wave from left to right, but complete isolation for the opposite direction. Of course, the system requires at least one polarizer in the case when the polarization of the incoming wave is not defined at the beginning. So this brings me to my conclusions. Quantum computers are essential for tasks beyond the reach of classical electronic computers and open various vital applications. Unidirectional signal propagation and routing are key technology required for quantum computation devices. The presence of dark state is crucial to establish large non-reciprocity in quantum nonlinear non-reciprocal devices. A novel approach to tunable isolation based on twisted bilayered Weyl semimetals is proposed in our work. The approach enables highly efficient tuning of both direction and value of isolation with the relative rotation of Weyl semimetals. Yes, and I'm really sorry that I couldn't do this presentation in person this year. Please feel free to contact me with your questions at any time via my mail shown on this slide. Hopefully we will catch up with you next year or at other conferences. Thank you very much for your attention.